So I mean, okay. So it was actually fun to think again about these topics. So I will talk about impredicativity, and it will be a very informal talk. So let me share the screen and find. So do you see the slides?
Yep.
Yep. Okay, good. Okay, so let me start. So, so this talk, so I will try to describe a calculus that I designed 84, 85, and I mean what's more important will be the questions and the sources for this work, because I think it's still relevant now. So thinking about what I'm going to present, actually, I found one main message. Actually, it's the importance of notations, and especially so the new notations that was introduced by Nicolas de Bruijn, where proofs are first-class objects. And actually, in the paper of de Bruijn, in general, so there are so a lot of very interesting discussions about notations. So like, I mean, what happened when people introduced notion of variables in mathematics, or I mean, notation of Leibniz for integral and differential calculus. Or, I mean, an example also that de Bruijn was found to mention was the introduction of the notion of functions. That was, for a long time, that was a meta notion in mathematics, and that was internalized in mathematics. So people introduced notation for functions like lambda calculus, and I mean, to have a primitive notion of functions in mathematics has been a great source of progress. So I think hopefully, so there's new notations that were introduced by de Bruijn actually will have, for where proofs are first-class objects, will also have a big importance in the future of mathematics. So this talk, so the first part, so it will be why it is nice to use impredicativity. Second part will be about paradoxes, and the third part will be what happens if we don't have impredicativity. So the context of this work, so it was about representation of proofs in a computer, and the ultimate goal was, I mean, what we want. So we should be able to program a computer so that the computer will generate interesting new concepts in mathematics and new proofs. Okay. And this is still the goal, but the partial goal will be that to have a computer that checks the correctness of a given proof. And also a computer should provide help in analyzing a given proof. So for instance, I mean, something that's quite simple but useful is when we have finished the proof, we can ask, I mean, if we have a formal representation of the proof, we can ask how many times some lemma has been used in the proof. And this is quite useful actually, because for a big proof, it's difficult to have this idea, and then it will actually shows what were the lemmas that were important, and we will learn something from it. And this example, actually, it was already in the first formal representation of proof. That was already something that Frege was noticing at the end of his book, actually. Another thing that I was really interested in was, so when we learn proofs in mathematics, so often we get some understanding by trying to instantiate a very general result on a special instance. So we get a special instance of a general theorem, and then we can try to simplify what's going on in this special situation. And in general, so we learn something from this. And so what I really wanted was to have a computer system where the computer helped in doing this. And we are almost there, but not quite actually. And so a text, I cite a text actually on, using the system of De Bruijn automate. That was by Uting, so which is available online, which is really a really nice example of use of formal representation of mathematical text in order to get a better understanding of the text. And the proof is simply a proof of a basic result, so pigeonhole principle, but from basic axioms. And Uting gives different developments. So first an informal proof, and then a more formal versions, and then the third step is almost completely formal version. And I found this, I mean, really, really interesting. So that was one context of the work, but actually the other context was different, and but they got merged. And it was so the master thesis that I got, which was about connected to System F. So System F, it's a quite remarkable extension of simply typed lambda calculus. And it was designed independently by a logician, so Jean-Yves Girard, and a computer scientist, John Reynolds, and with completely different motivations. So for Reynolds, the motivation was to extend the simply typed lambda calculus. So problem with simply typed lambda calculus is that we have identity function, but we have one identity function at each for each type. So we have lambda x naught x, lambda x bool x, and so on. And so what we want, and that's an idea that comes from computer science, we want to capture the idea of polymorphic algorithm. So this comes from Strachey, actually. So we have the idea of, for instance, a polymorphic sort. So a sort can be generic in the ordering. And a simpler example is a polymorphic identity function. And this is how a polymorphic identity function is represented in this calculus. So it's lambda x alpha alpha, where alpha is a typed variable. And the type will be the following. So, and this means, so for all type alpha, we have a function from alpha to alpha. And this is something that we may want actually in a programming language. And actually that's something that no Haskell has. I mean, the core Haskell use this system. But what was very mysterious at the time is that so this calculus has no apparent set theoretic semantics. So in set theory, so there is no type, no set of polymorphic functions, because this, if we take the product over all sets of x or x, we get a set which is too big to be represented in set theory. Yeah, I forgot to say, please ask questions at any time. Something is not clear, because I think I will mix quite a lot the levels of things in what I will present. So there was no apparent set theoretic semantics. And then what was quite exciting at the time actually was so where I was working. So John Reynolds was visiting, and he was giving very interesting talks. And so one talk that he gave actually in 83, he was conjecturing that it should be possible to find a set theoretic semantics for this system. And then 1 year later, so he discovered, but then it was a theorem, and a really nice theorem. So I will say more about this result, that there cannot be any such set theoretic semantics for this calculus. So it was quite exciting actually at the time to try to understand better this calculus. But at the time, so when one looked at this system as a formal system, it was quite complex system compared with simply typed lambda calculus. So in presentation of simply typed lambda calculus, so at the time, so one started, so for each type, one started with an infinite collection of variables for this type. So there was an infinite collection of variables of type NAT, infinite collection of variables of type NAT arrow NAT, and so on. And it was not so clear how to mix this actually with what happened in System F, where we have type variables. And actually, so if you look at the presentation of Reynolds of the system of System F, it was quite complex. And so there was also restriction on typed variables. So you could form this polymorphic program, and it is of this type. But for instance, you cannot form this lambda alpha, x alpha. So when you form this abstraction, there was a restriction that alpha should not appear free in subtype variables of M. And it was quite a complex, actually, restriction. So it was not so simple to go through this formal system. And Girard actually had an extension of this calculus. It was F omega. That was even more complicated with very complex notations. And when people presented the calculus at the time, so it seemed important to not to mix the order of in which we present the calculus. So we first present the types, and then we present the terms. And then we had problems of this kind. So that was context for about system F. And then, so what happened was actually at the same time, so I was reading about the system Automat. And this is really, I mean, nice system that was designed by Bruijn in the beginning of the 70s. And what's nice is that his papers actually are available. Most papers are available online. So they did an archive of his paper. And so what Bruijn wanted was to have a formal system for representing statement and proofs in mathematics. And he came out, so completely independently of Howard, actually. He came out with the idea of proposition as types. And as he said, so treating proposition as types, so it's definitively not in the way of thinking of ordinary mathematician, yet it is very close to what he actually does. So that's what I found actually very nice with De Bruijn works. I mean, De Bruijn was a mathematician and really, I mean, really impressive mathematician. But he was interested in analyzing actually the structure of mathematical statement and mathematical proof. And so that's the example that he gave. So for instance, so that's an example, I mean, artificial example of a statement that you can find in a mathematical text. So theorem 1, so let x be a real number, so that f of x is strictly bigger than 1. And let n be a natural number. So if we have g of x strictly bigger than x to the n, then f of x is strictly bigger than n. So this is an artificial statement, but it looks like I mean, the statement that you will find in a textbook in analysis. And if a mathematician wants to use such a statement later on with a value for x, so for instance, x equal pi, a value for n equal 5, so what he has to do is to give first a proof that f of pi is bigger than 1. Then he has to give natural number 5. Then he has to give the proof that g of pi is strictly bigger than pi to the n. And then he can state f of pi is strictly bigger than 5. By applying theorem 1, and by giving, so, and what was important is by giving in this order, pi, the proof 1, 5, and the proof 2. So then, so what De Bruijn discovered is that if we look at the mathematical structure of text, we have actually interleaving between mathematical object and proofs. Okay, and so he introduced so his notation, so that in Automat, so this will become so corollary. So we apply this theorem, and we apply theorem 1 to pi, 1, 5, and 2. And 1 denotes a proof that something about pi, and 2 denotes a proof about something about pi and 5. And once again, so what is important is the order in which we do this proof. And a crucial notion also that was in Automat, that comes from computer science, and that was inspired from the notion of block structure in Algol 60, is the notion of context. And this is a notion also that I found, absolutely essential in the representation of logic and mathematical proofs. And it's nice. This is something that comes from computer science. So what is a context in Automate? So it was a sequence of variable declarations with their types and named hypotheses, but in an arbitrary order. So for instance, that's a formal representation of the statement that I showed. So we have a real number x. We have a proof that f of x is bigger than 1. We have a natural number n and a proof about this natural number and x. And this is the context of the statement, the context that we are forming when we understand the statement. And Automate had also a primitive sort for a type, and then this formal statement will be in this context. Okay. So, and this idea of mixing proofs and term, so this is something original to Automate, and actually which applies to System F, and which actually solves this issue that we had with the complicated presentation of System F. And in Automate, we could also introduce a primitive sort prop, or we could take, we could adopt completely this idea of proposition as type, and we could represent proposition as types. Okay, so I give, and Automate also had a curious notation that I will use actually in the slides, but this notation has not survived, but I found it actually quite interesting, and it should still be explored, I think. It was to use the same notations for long typed abstraction and for dependent products. So the formal system, so of the terms of Automate, was quite minimal. It was this, only this. So a simple type lambda calculus. So we have variables, applications, and we have typed abstraction, so like this, but also a dependent product. So this can be read both as lambda x of type A, M, or pi x in A, M. And then we have the sort type. And then we can mix terms and types, so that's this idea of mixing actually types and terms. So that calculus is quite minimal. And one of the first examples that De Bruijn presents actually, it's an example of equality. So equality on a type A. So in Automate, so this was represented as a primitive symbols. So we could introduce in Automate primitive symbols. So the equality will be a symbol of this type. So which means that an equality of type A takes two elements of x and y and produce a type. Then what is important about this relation is that it has to be reflexive, and it has to satisfy this axiom, which comes from Euclid. So that this axiom that if we have x and y that are both equal to z, then x and y are equal. So that will be the formal representation of what is equality in Automate. And that was introduced as primitive, but then we can prove from this, there's primitives, we can prove that equality is symmetric, and that's a formal representation of the proof in Automate. And I think it's the first example of De Bruijn actually, so that if we have x and y, and we assume that we have AQ of xy, then by using by using type lambda calculus and applications, so we can apply this primitive to y, x, and y, and the proof that y is equal to y, which is reflexivity applied to y, and the hypothesis that x is equal to y, and we get a proof that y is equal to x. So it was quite nice, to have this very simple calculus in which we can represent formal proofs. Okay, so that was the context of the work. So on one side, so it was to understand better System F, and on the other side, so there was this nice calculus for representing proofs. So, I mean, the idea was quite simple. It was to simply to try to combine, nice notations of automat and with system F. Okay, so just to give, some examples that was of the kind of things that were not so easy at the time. So, for instance, we had I had seen writing rules for intuitionistic logic, but it was a list of axioms, and I had no understanding, of these axioms. So, one typical question I had was, so why do we have A implies not A in this list of axiom, and why don't we have not A implies A? So that was something, it was not clear for me. But using, automat notations, it became completely clear. So what is notation in intuitionism? So not A is A implies axiom. And then what is A implies not A? It's A implies this, okay? And then if you write this in automat, then it's clear that, you can build a function of these types. So lambda x A, lambda f A implies absurd, and then you simply apply f to x. So it's clear that you should have A implies not A. But then if you have not A, so if you have this, it's also clear that you cannot build any term of type A, because everything that you will build intuitively, so everything that you will be doing using this variable, it will be something ending with bottom, so it cannot produce something of type A. So it was, you cannot have not A implies A. So then it became, the rules of writing that were looked formal before became completely transparent with this notation. So that's an example of something that I said at the beginning of importance of good notation. So as I said, calculus automat is very, very simple. So you have variable, abstraction, and then application. So it cannot be simpler. So what was the idea? So the idea was, to combine the automat and system F. So to allow quantification over this special symbols that you can build in automat. So you have the sort type, and then you can have you can build the type. So x in A type, x1 in A1, x2 in A2 type, and so on. So in order to get system F, it's simply to allow quantification over this. Okay, so that's a very formally a very simple extension of system F. So we allow quantification of our sorts of this form. So for instance, so A type A, so and we interpret this as dependent product. So it's considered to be a type. So exactly like in system F, where we have for all alpha alpha, which is a type. So so that's very simple to extend automat with system F. And so this possibility was actually mentioned by Bruijn in the first paper on automat. But then, just after this mention, Bruijn said, so it is difficult to see what happens if we admit this extension. So, but given, this work on system F, it was a quite natural idea to extend it. And then to explore what happens if we extend automat with this. And then so for instance, one surprise was that we get in this way, we get not only system F, but we get F omega. So the system that looked so complex in Girard, actually, habilitation thesis was actually got formally very simple. And it was even more suggestive. So if we used some idea of automat, so that had not survived also, that is not used anymore now, but I think should still be explored. It was to present the system in this way. So we don't present, the judgment is not M of type A, but the judgment is M is a correct proof or a correct type in a given context. And then, so if we do this, I mean, the proof for type abstraction and type quantification becomes the same, and it becomes a simple shift of context. So formally, it becomes very, very simple. So the rules for forming context are very simple. So if we build A and A is a correct type, then we can add a variable of type A in the context. If C is a correct context, I mean, ending with type, we can add a variable of this type in this context. The rule of application is like this, but we should check that the application is correct. And how do we do this? Well, we compute the type of n, so, and it should be a type product. And we checked that the type of m is compatible with the type that n expects. And so we have to introduce this subtyping relation. That was a notation of automat also. And this is very simple formally. It's that if we have a type of this form, so a sequence of product ending with type, then it is a subtype of a gamma type. So we can always shorten a sequence of type ending with a sort type. And then it's so it's impredicative if we allow A1 and N to be arbitrary, and it becomes predicative if we restrict AI to be of type itself. And then De Bruijn had also another interesting notation. So he was suggesting actually to write application. So instead of writing it on the form M applied to N in this way, he was suggesting to write the argument on the left of the function. So this should be written N in this way. So M come first and then N. So the argument comes before the function. And with this notation, so which is non-standard, but which is actually very nice, the computation of the type of a term becomes very simple. So you have the term M, you look at the head variable of this term, and with De Bruijn notation, so this head variable, it's at the end of the term, and then you replace this variable by its type. So for instance, I mean, you have this, so that's identity, polymorphic identity. What is the type of this? Well, you simply replace X by its type. What's the type of X? Well, the type of X is A, so you get this, which is the type of polymorphic identity. So another example, so this is lambda F, lambda X, F applied to X. What's the type of this? So you replace F by its type, you get this, and then this becomes a redex. So it's lambda Z A applied to X. So a beta redex is something of this form. And this is a really nice notation because you see the M is very close to the variable. So, and that's how a redex should be. I mean, the variable should come with the argument. And if X is not free in N, beta reduction is a simple simplification. This becomes N only. So this is what happens here. So Z is not free in A, so this simplifies to A, and indeed, this is the type of this lambda term. So this, sorry, yeah, question, yeah.
Yeah, I mean, this is a nice notation, but in the end, I mean, in the abstract syntax, this is identical, right? I mean, if you write the argument on the left or on the right, it's,
right? Yes.
It's
yeah.
just the abstract syntax.
Good point. Yeah.
But yeah, I mean,
yes.
This is maybe just convention.
Yeah. No, but I think it's nice to think about it. Yeah, but you're right, completely right. That in the abstract syntax, it's not there. Yeah. So more traditional presentation of this system is the following. So you see it. I mean, it becomes as soon as you introduce distinctions between. And this should be a typed abstraction like this, actually. So I have a typo. So this should be written like this. So as soon as you want to be more traditional, I mean, you want to make a distinction between lambda abstraction and pi abstraction. I mean, the calculus becomes more complex actually, so but becomes clearer also. So that's the rule of the system where you mix actually system F and automat. So it's not too complicated, and actually terms are understood to be up to beta equality, and actually up to eta equality, beta eta equality in automat also. So that was the calculus that I started to analyze, and so sorry, one question.
Question, yeah. What's C here?
Sorry, what?
What is the C here?
Yeah, so C. So the syntax of the term is this, but then in this class of terms, so I want to distinguish a special class of terms, so that are the terms that are a sequence of abstraction ending with a sort type. So that's and this will be used so to give a type to types or to operation on types. So the sort in F omega, in the system F omega, and I need to distinguish this subclass because I need this rule actually for typing. I need a special typing rule for these symbols and for extension. So I have two ways to extend the context. So I can extend the context either with a variable of type A where A is a type, or a variable of type C where C is a correct expression of this class. Okay. So does this answer the question?
Yeah, it does.
Yep. Okay. Yep. So that was the calculus. So then we can write, I mean, as usual, so we write A or B for, but I still like actually notations from automat, so I will use it in the slides, even if it can be confusing at some point. So as usual, so we write A or B for lambda x of type AB if x is not free in B. So this is a type of polymorphic identity, and polymorphic identity is this lambda term, which is of this type. And this is, I mean, how does the type checking works? Well, it's simply, I mean, x is of type A in this context, so this is correct. And and then actually formally, what you get is a calculus in which you can formally prove that you can embed system F in this calculus. And but what become really nice actually is that I mean, there is no problem with restriction on variables for for-all introduction. I mean, you had this weird restriction on the for-all introduction, but there it becomes completely clear. I mean, it becomes because of the use of this context facility. I mean, the typing rule is very simple. So this is taken care by the notion of context. And also what I found really nice coming from automat. So I said, so in usual presentation of simply typed lambda calculus, you start with this infinite collections of variable at each types. And this was not so elegant. So with this notation, actually at each given time, you have only finitely many variables that are alive. So that are the variables that are in the context. And this also I found very nice. That, I mean, this was a really nice addition to usual presentation of logic coming from automat. And then, also, so what happened is that, so you had this encoding coming from logic. So you can encode everything. So for instance, absurd, you don't need to introduce absurd as a primitive like in automat. I mean, absurd proposition can be defined as pi a. you don't need to introduce a primitive for conjunctions or for product, because this can be defined, this can be encoded in system F. So like this. So equality, that was a primitive in automate of this type, polymorphic equality, well, it can be defined in this way. So that's coming from Russell, actually. That's encoding of equality. So to say that X is equal to Y is to say that every property of X is a property of Y. And then at the same time, so there was actually encoding from coming from Church and from Girard and Martin-Löf and Berarducci of data types in system F. So you could encode a bool in this way. You could encode a NAT in this way, and Berarducci, so also that you could encode a list. So it looked like you didn't need to introduce any primitive to this simple calculus. Everything could be defined from nothing. So you could define everything in logic, and you can define everything in programming language. So that's really the positive side about impredicativity, that everything can be defined. So there was a simple and uniform notation. It contains system F omega. It contains a Church system for higher order logic. And from automate, you get a uniform treatment of functions and proofs. Proof checking becomes type checking. And this can be represented quite simply, relatively simply. I mean, at the time, it was not so easy, but it was really nice. I mean, at the time, so Girard Ruet was developing ML, precursor of was developing ML and data types, and it was a really actually a simple representation of this calculus in ML. And so as I said, so you could represent, not only you could define the absurd proposition bottom, but you had a really simple proof that from absurd you can derive everything. So that's this statement with this notation. And the proof is simply you take X and you apply it to B. And this is because the type is this, which is this. And you can see that actually it's simple to see that in this system, so you have to prove that bottoms implies bottom. This term and this term. And contrary to Martin-Löf system, so where you have to introduce primitive data types and extra computation rule, so we didn't have to assume anything. So as I said, so data type could be defined, logical notions to be defined, and you can define, so for instance, you can prove that equality is reflexive, and it has a simple proof. So also what was important was that, like in automate, so this was decidable. So you had really a reduction of proof checking to type checking. And so this was not the case for Martin-Löf system at the time. So Martin-Löf system at the time, so it used an equality reflection. And the judgment, so with this equality reflection, the judgment M of type A was not decidable. So hence the system, Martin-Löf type system at the time was much more complex to implement. So there was an implementation here in Göteborg, so but it was I mean, really nice work and really nice implementation, but it was not reducing proof checking to type checking. It was using a LCF approach. And the same, so there was an implementation in New Perl, but New Perl was also using this equality reflection. And then, so if you use the equality reflection, so it was not clear actually what was the meaning of M there in a type system, because you had an unclear status for terms. So these terms were not really proof, because you cannot check if they were correct or not. So they were not complete proof. So so the situation was interesting also compared with what was Martin-Löf system at the time. So Warwick, so how shall we do about times? So should we have a break at this point?
Yeah, sure. I don't know, maybe 5 minutes.
Yeah. So
if you want,
good,
yeah.
45, yeah, okay. So, okay, good. So we have a break and we resume at 4:50, yeah, okay, good.
Yeah, I'll pause the recording now.
Yep, good. Slides again. So do you see the slides again? Yeah.
Yeah.
And then I don't remember where I was. So let's see. Yeah. So that automate. Yeah. Yeah. Exactly. So that's what is actually that's the first part almost. So what was really nice about with impredicative system, and also what was that you it looked like you could deduce everything from nothing, and you could define every logical symbols, every logical connective, every data types could be defined, and that looked really nice actually. So what I will describe now is what happened when you started to use this system. So, and the first example that was encoded in this calculus actually was a result proved by Frege, so in his book. And so this is, I mean, something absolutely incredible in logic. So he had his system was based on implication and negation. And I will not give actually the rules for negations, but he had the axioms that he had for implication was exactly the type of S and K, I mean the combinator S and K. So contrary to what was done after. So he had understood, I mean, the deduction theorem, and it was really, really nice. And then what was remarkable in Frege's work is that it was the first to introduce quantifiers and higher order logic. And the rules for quantifiers, so there was this rule, this axiom, that's quite reasonable. If you have 4x phi, you have phi of t. But then a crucial rule, which is, I mean, absolutely remarkable, is the rule for rule introduction. And it's the first time actually in logic that there was a discussion about free and bound variable. So in mathematics, so there was already this discussion for integral calculus and Leibniz notation. But the rule of for all introduction is this one. But we have the side condition that x should not be free in phi. Okay, and that's exactly the same restriction that we had in actually in the system F. And what is absolutely remarkable, and this is something actually I learned from 2 years ago, I mean from Jan von Plato actually, who is historian of logic, is that I mean the fundamental contribution is that one can capture in a finite way with this rule the laws about quantification over a maybe infinite collection. And so I think we are so used to this rule that we don't realize how important this contribution was. And what I found remarkable in automate notation is that actually this rule is captured by this. So it's simply a shift of this, I mean, type X of type A. Okay, that's a rule which captures this, and we don't have the condition on the freeness with this notation. So this rule, which is fundamental, becomes even simpler with this notation. And so what Frege did in this book, it was to show that the transitive closure of a functional relation defines a linear order. And so what was really nice, and it was the same feeling that we had when developing, I mean, the deduction in this impredicative calculus, is that we could deduce in a purely analytical way we could deduce things that looked relying on some intuitions. Like, for instance, this statement. So it looks like for a mathematician, in order to prove it, we have to rely on some intuitions. But the point of Frege is that no, we cannot. Only using formal rule of logic, we can do it. And Frege had so this impredicative encoding of transitive closure of a relation. So in this calculus, it's possible to encode transitive closure. How do we encode it? So it's as an intersection of all transitive relations that contains R. And this is represented in this way in this calculus. So it's very simple and natural to represent actually inductive definition in this system. And we can represent so all inductive, co-inductive definitions, also co-inductive definitions. So a co-inductive definition, it's the greatest fixed point. And this is also representable in higher order logic. And so another example that's possible to represent, that was a notion of well-founded relation. So it was possible to define it in this way. So simply expressing the principle of Noetherian induction. And so it was, as I said, so it was possible to encode equality. And there was two natural actually encoding. So one was as the least reflexive relation, so that's this encoding. And the other encoding was as, so the encoding I already presented, that every property of X is also a property of Y. But as I said, so it was also possible to represent data types. So for instance, the type of ordinal, so it was very simple to represent it in this way. And we could program so functions of type ordinal to NAT or NAT. And we could define in this system, so you had, I mean, people had designed ordinal notations, and it was possible without any problems to encode very large ordinals in this system, and to encode actually a large collection of functions from NAT to NAT, actually. And in system F, I mean, you had more functions from NAT to NAT that you could encode than in Martin-Löf type theory. And all these functions were terminating because you had this normalization theorem and decidable type checking, which was connected to decidable type checking. So all this, I mean, seemed really, really nice. But now I comes to the first problem with this impredicative representation. It was, so what you get with this impredicative encoding is that we get, in a natural way, so you get a representation of iteration, so this. But what you want, so for instance, for defining the predecessor function, is you want primitive recursion. So you want to encode this schema. And this you don't get naturally with this encoding. But it was not too bad because you can build a product of types, as I've explained. And then using product of types, it's simple to reduce primitive recursions to iteration. And actually, in this way, we covered very clever encoding of Kleene that was done in lambda calculus without this help from types. So this was a problem, but it was not so serious, actually. What was more serious was that so it was not possible to show the induction principle. So I explained the encoding of NAT, but then you can express induction principle in this way. So, but very, I mean, it's very easy to show using normalization that this is not impossible to prove in this calculus. And actually, a really surprising result that came later was that you can even show that there is no possible encoding of type of natural number where induction principle becomes provable. So, but at the time, it didn't seem to be such a big issue, but because instead, what you do is that you reduce yourself to a natural number satisfying this predicate. So you see, it's very simple to get from there to there. It's a simple shift of this abstraction. So you put this abstraction at the beginning, and you get a predicate on natural number. Intuitively, that's a predicate of being built, well built. And the natural numbers that satisfy this predicate satisfy induction principle. And it's very easy to show that 0 satisfies this predicate, and that if a natural number satisfies this predicate, the successor of this natural number satisfies this predicate. So this was not, it was a problem, but it didn't seem such a big problem. What was more, actually, and this is very similar, actually, that's something that came later, internalization of parametricity predicate in this calculus. But also another thing that was more serious is that one cannot show that 0 is different from 1 in this calculus. And it's actually possible to show that this is not provable. But still, it was nice to explore this representation of inductive definition in this calculus, and in a systematic way. And one really nice work, actually, that was the work of Frank Fenig and Christine Paulin, where they study systematically this encoding of inductive definitions. And so, I mean, an example I found nice is the encoding of F2 in F3. So that was quite clear, actually, using these notations, but and the idea of mixing proposition and types. And I don't think this would have been discovered, actually, without this mixing of proposition and types. So what's this encoding is that actually it's, so that's, so if we think of proposition as types, so it's encoding of inductive family with the following constructor. So it's an inductive family on type, family of type, where we have this constructor. So, so it's very natural to think of this as an inductive defined predicate. But this can be thought of as a family of type. And when we think of this in this way, what we get is an encoding of F2 in F3. It was a really nice discovery of Frank Fenig, actually, in this. And then we can start to study encoding of a formal system into itself. And that was really nice. And actually, I should mention, so it's a parenthesis. Encoding can be really interesting in a univalent setting. So I don't want to go into the detail, but I mean, this is the encoding of the circle. And we can encode also integer, so not only natural number, in this way, using this type in this, where this is a type of equivalence. So the, I mean, this encoding actually is still interesting now. And then, so there was actually at the time also there was a really nice letter from Plotkin to Reynolds. So I get a copy of this letter from Girard and that was so general pattern in all this encoding of data type in system F. So what we have, so I mean that's idea coming from category theory. So we have a functor, so from type to type, and what we, the data type is the initial T algebra for T. So and what is a T algebra? So it's a type X with a map from Tx to X. And the general pattern is that, so this is a representation, almost a representation of the initial algebra in this system. And provided we have this, so T at acts like a functor, when we have this encoding, so it's very simple to define intro of this type, TA out A, and a match function, so from A to TA. And so this is Lambek's argument in category theory, but it's quite concrete and with these notations actually. And it's a general pattern that I found, that notations from a type lambda calculus are really nice actually for category theory. So complex argument in category theory, I mean, for me, becomes very simple when expressed in these notations. Okay, and so what is nice compared with, I mean, the non-impredicative, so the predicative representation of data types, is that it's completely flexible. So we don't have a syntactic restriction on T. I mean, this works for any T, and the only thing that we have to check is this. So this is much more elegant than, I mean, the primitive representation of data types. But I mean, as you know probably, and as we are going to see, unfortunately, so this is not a complete solution. Okay,
But
so sorry, yeah, question.
Isn't match again this predecessor function?
Yes. Okay.
So you have to go through the product trick, or?
Yeah, well, so actually, in this abstract framework, you don't need it. I mean, the argument, so if you give T, it's very simple. So you have intro is of type TROA. And then since T is supposed to be monotone, you apply T to it. So you get something of this type. And then since you have TA and something of this type, you get match functions from A to TA. So it's very, very simple to define this match function. And this is exactly what's, I mean, Lambek argument about initial T algebra. So there is this trick, and so what's interesting in this is that there is a double meaning of this T. So T is used in this expression, so T is used both. It's the same T at on the left and on the right, but it's used in a different way. So about your question about match for natural number, I mean, what happens is that for natural number, so you don't have actually a T. So for this T, you need 1 plus X. So that's how you will represent natural number, but you don't have this plus as a primitive, and that's where you get a problem with the predecessor functions. But if you formally, so you do Tx equal 1 plus X, and you can rewrite this with this is isomorphic to this. So then you get an encoding. In this way, you get the encoding for natural number. So as was found later by Gavin Reth, I mean, this works even for co-inductive data types, so for streams. So for instance, what will be the type of stream? So it will be this, if you add an existential statement. And in general, it will be this. And you have an existential statement because you have you can encode existential quantification. I mean, this was standard in logic. Like if you have universal quantification, you can encode existential quantification.
Can I ask a question?
Yep.
In the 2 slides ago,
yep.
You said provided we
yep.
have this, and then on the next slide you showed this T.
Yeah.
But there are 2 ways to implement that type, because I can always return unit.
Yep.
Or I can have the proper.
Yes. Yes. Yeah. Yep.
And 2 different data types.
Yeah. So indeed, so the argument that I worked, I mean, is it will work for any such function. So, but then if you don't use the correct one, I mean, you will not get the correct match function. Yeah.
Okay.
So
Consistency is not
yes
an issue there.
Yeah. So actually, this will come out later. Yeah. But formally, I mean, in the calculus itself, for defining a function of this type, any function of this type will work. Actually.
Okay.
Yeah. Good. Okay, so you have an encoding of existential quantification, and that was also interesting. So you can encode exist, and you could program first projections, but you could not program the second projection.
So may I still add something to this match question? So maybe, yeah.
Yep.
I mean, I think I follow you, but the match doesn't compute in constant time, right? It's the
yeah,
which actually iterates the whole structure, right?
right. So yeah, for yeah, most of the time, yes, I think yes, you're right. Yeah.
That was the problem with the
Yes, that was,
predecessor.
yes, yeah, that's
Linear
what we,
time in this.
yeah. So, but actually, I mean, the question actually, how good is the representation of the predecessor, is a very interesting question, because I mean, there are some arguments actually for which this representation is good. So, I mean, I don't want to extend on this, but it's actually a very interesting question. Yeah, but you're completely right. I mean, if we this will be a problem actually. Not so good representation. So that's another problem with this impredicative representation. We could represent so existential quantification on type, and that's a formal representation. But in this way, we don't even have the first projection. So we have no projections. So this looks good, bad, but actually there are there are arguments actually for not having the first projection, and it was a really nice paper by Mitchell and Plotkin that was to use these existential quantifications for encoding of abstract data type. So the fact that you cannot have the projections, it's connected actually to this fact that you have hidden the representation. So you have packaged the representation of this type X, and you don't have access to it. So this is actually maybe interesting for representation of abstraction. Okay. Yeah. So something else, yes, that I want to say, and that's connected actually with the representation of Martin-Löf, so equality reflection. Is that so in automate? So you had this notion of definitional equality that was beta-eta conversion. That was different from the book equality, that was propositional equality. And so this distinction was, forgotten in Martin-Löf equality reflection. And this notion of definitional equality also was not present in Frege, and it's not present in higher order logic, usual presentation of higher order logic. But actually, why I was representing proofs in Frege, so, I mean, my feeling was that terms represented exactly the proofs, what I had in mind actually when I was trying to understand the proof. So with this actually notion of definitional equality. So I didn't want this definitional equality. I mean, they were not part of my mental understanding of what was going on in a proof step. So, and furthermore, so I mean, this is really good notations for proofs, and that was what I was looking for. So because we can use actually beta reductions to do instantiation proofs. So we could, in theory, we could use these notations to take a general proof and then instantiate it on a particular case, and then start to simplify the proof in these special cases. And this is something actually that should be present in proof system. I mean, in Agda, and we should be thinking about how to do this, because I think this is really something that's how we understand proofs in mathematics. I mean, we try to run a proof in special cases, and we should make use of this. I mean, the fact that we have lambda calculus notation for proofs. Okay, so now that will be the last part of this. So that's about paradox, and also more problems with impredicativity. So this calculus looked really nice, but was it consistent? So it was not clear at the time, actually, and so I discovered later, I mean, that actually for the calculus I showed, there is a completely trivial proof of consistency. But why it was not clear? It was because I found out, so Martin-Löf had introduced a very similar calculus that looked almost the same, but instead he had a type, so type, column type. So the calculus was even simpler, so even that nicer than the calculus we get by combining automat and system F. But Girard found a contradiction if you had the type of all type. So actually, and this contradiction was not so easy to follow actually. But still, looking at the proof, it was clear that the calculus I showed, so becoming consistent if we introduce a sigma types like this with two projections. So actually, it was very important that we could encode existential, but it was crucial that we didn't have the two projections, because otherwise we could have been able to derive a contradiction. So then it was actually not so clear that the calculus was consistent. I mean, what was the difference? Why? So it became important actually to analyze the paradox. And remark is that so also at the time, so Girard had discovered this paradox, but Martin-Löf had a consistency proof for his system with type, column type. And this proof was formally correct. I mean, the proof, the idea was the proof was correct, and the proof was formally it was okay. So how was this possible? I mean, that was the situation at the time. And then I discovered actually there was a lot of history behind this question. So that's a question of impredicativity. So after Russell actually found the paradox in Frege's system, so he introduced stratification in types for avoiding this paradox, but the impredicativity that we had was not something that was so obvious. And so that this, when we do for all alpha, so this proposition, the fact that it is a proposition that we get by quantification of all proposition was not something that was so clear. Actually. And this problem actually becomes even more apparent in system F. So in system F, so we have polymorphic types, but then using polymorphic types, so we can build this is correct term in system F. So lambda x of type bottom, so where bottom is for all alpha, then we can build this term. This is a correct term. And I mean, it looks dangerous because it looks very similar to lambda x applied to x. And that's how we build a non-terminating term. So there was, I mean, there is some actually doubt about normalization for system F. And then there was a lot of work actually connected to system F before, so in logic by Thierry, Prawitz, Martin-Löf, and Bruijn, that were connected with consistency for higher order logic. So it was clear from Gödel, it was clear that the proof cannot be elementary. And the discovery of Girard actually was that so normalization of system F, omega implies consistency of higher order logic. And Girard in the 70s, he found a very elegant proof of normalization for system F and F omega. And this proof was analyzed by Martin-Löf. And that's by analyzing this proof of normalization, actually, that Martin-Löf found this normalization proof for the system with the type of all type. But actually, by Gödel, once again, so in doing such a proof, one should use a stronger system at the meta level. And that was the situation, actually. So what was discovered, and that was the discovery of Martin-Löf, is that the most elegant possible normalization proof is obtained when the meta logic is as close as possible as the system itself. So it cannot be the same as the system itself, it has to be stronger, but it's most elegant when it is almost the same. And And that's how, actually, that's the best way to understand the proof of normalization in F omega. And that's what Martin-Löf understood. And when we do this, actually, for a type system with a type colon type, this works as well. But at the meta level, we use a type of all type. And this, I think, has been really, clarified by the work of computer science work. So, Jean-Philippe, Patrick, and so I don't know actually, last Patterson. So work they did here at the department. So this work on parametricity. So actually, so in this system, it's very clear actually, and very nice how to build systematically a proof that term is parametric. So for instance, the fact that the identity function is parametric, it can be internalized as this term. So and there is a very simple transformation that goes from this term to this term. And in this way, we get a proof of parametricity, which is completely obvious, actually, in this, so it's a really nice work. And that was what was going on, actually, in this proof of normalization and canonicity. It's this trick, this internalization of parametricity that's underlying this. And what happens is that this internalization of parametricity works with a type of all type by defining a type prime. So when is a type parametric? Well, to be parametric for A, it is actually A implies type. So that's what happens. So that was, conclusion of all this. So that was the explanation why Martin-Löf could prove formally canonicity for his type system. It's because at the meta level, he was using a type of all types. But this applies actually for all systems that are strong enough. So as soon as the system is, stronger than primitive recursive arithmetic, or even for predicative system like Martin-Löf present system, we cannot learn anything from the proof of normalization. So that was the conclusion of these works, actually. So we can prove normalization for the system, but we cannot get this as a proof that the system is consistent, because, that's Gödel's theorem. At the meta level, you have to use something stronger. Okay. So, but on the other side, so when you have a paradox, a paradox is something very concrete, and then it can be tested. So that's a difference. So you can never be sure that the system is normalizable or consistent, but you can be sure that when the system is contradictory. I will end by trying to describe this paradox and what we could conclude from it. So Girard didn't find this paradox while looking at the contradiction with the type of all type. And actually, I don't think this would have been possible. Given Martin-Löf proof, I don't think this would have been something natural to look at. What he did instead was to look at another system and then to find that this system was contradictory, and then to realize that the type system with a type of all type was interpretable in this other system. And what was this other system? So it's very natural, actually. It's to extend system F. So system F is a system for typing programs. And as I said, so Haskell, for instance, use this type system. Haskell use even F omega for representing programs. So it's very natural to want to reason about Haskell program. So it's very natural to want to reason about term system of system F. So it's very natural to extend system F with a type of propositions, or F omega with a type of proposition. And actually, so Girard's discovery was that this is not possible if the type of proposition is itself a type of this extension of system F. Okay. And contrary to the contradiction with the type of all type, this is not surprising actually, because if you have, I mean, that's connected with the fact that system F doesn't have a set theoretic interpretation. So it's quite natural that if you extend system F with a type of proposition, then you will get a contradiction. So what was the extension of system F? You had a type of proposition, and then you had possible quantification. So one is that you can quantify over types. So like in system F, so you have for all alpha. So then you can quantify over for all alpha phi, where phi is a proposition. You can quantify over types also. So you can quantify over the sort type. You can quantify over types because you want to reason about programs. So it's natural to quantify over types. And then you should be able to form implication of propositions. So you can also form this. And Girard designed a system where you had 1, 2, and 3. And then he conjectures that probably the system where you don't have 1 should be consistent, was maybe consistent. And what I found out actually is that so you don't need 1 to get a contradiction. Even using only 2 and 3, you get a contradiction. And so that's what I want to explain, because it's actually connected to Reynolds' proof that you don't have a set theoretic model of system F. So, so Reynolds were using this encoding of data type that I described, but he was using this encoding for this functor T. So T of X is X arrow prop. Okay, so since it is covariant, actually this is covariant, so if you have X implies Y, you have T of X implies T of Y. So hence you do get intro function, and you get a match function also. And there, so the question from Andreas actually becomes very interesting, because contrary to the type of natural number, I mean, in building these T functions, you use only implication. So then the match functions becomes not so good, but not so bad actually. And that's what happens actually in this paradox. So what was Reynolds' intuitions is that so this this type A, it should be almost like initial T algebra. But then if you have an initial T algebra, intro and match are isomorphisms. So you should have an isomorphisms between A and A arrow prop. Okay, but in set theory, so prop is a type 0, 1. It's a type bool, and it's clear that you cannot have an isomorphisms between A and A arrow 2. So that's, you should get a contradiction. And so you don't quite get an isomorphism, but you get an isomorphism. I mean, if you by using something which is essentially what you do when you prove so theorem in category theory, which is Frege's adjoint functor theorem. Actually, what you do is that if you restrict yourself to elements of these types that are polymorphic and parametric, so that's this idea of parametricity once again, then you do get actually initial algebra, T algebra, and you get a contradiction. Okay, so that was what I did. So I started from this argument from Reynolds, and I wrote it in this calculus. And by using this parametricity like argument, I refined these data types to the subpart of parametric expressions, something which is expressible in this calculus. And then I get, when you restrict it to parametric arguments, you get that this intro function and match functions are inverses, and you get a contradiction. So Reynolds was doing this reasoning in set theory, but his proof works as well directly in type theory. And I found out actually only that it implies to Girard's questions when Bruijn had introduced notations for pure type system. So yeah, that's something. But what was really interesting was that later on, so Hurkens actually found out that we don't need to go via parametricity. And so this is connected actually to this Andreas questions to how bad is this match functions. Okay, but instead of using so this data type, so I was surprised to see that Hurkens was using this data type instead. So this is always possible. I mean, you can, instead of using X here, I mean, you can use T of X at this point when the T of X is X arrow prop arrow prop. So actually, while preparing this talk, I got curious and I thought, well, cannot you use actually this data type to and have a similar contradiction as the one in Hurkens? And I was really surprised actually that exactly, I mean, the same argument that Hurkens had, you can do it with this data type instead of this data type. So that was quite surprising. I don't know I don't understand what was going on actually. And yeah, and for doing this proof quickly, so it was, I mean, it's essential to have a proof assistant. And so it was really good to have Agda with the option type in type. So that was done very quickly. And so, I mean, the moral is that so this intro and match are not definitional retract. They are still definitionally good enough so that we can get directly a contradiction without going via parametricity. And that's Hurkens' argument, actually modified with this this encoding of the type paradoxical type, I mean, this T algebra. And so I only had to copy actually, so that's Reynolds, that's Hurkens' derivations. But I mean, starting from this, it's starting from this, it's the same as Hurkens' derivations, but I changed T of X to X at this point, and the same argument works. Yeah. So it's a very short contradiction and a very short paradox. And so if we think actually this idea of using beta eta reduction as a process of understanding a better proof, I mean, we can apply it to this paradox and we can ask, I mean, what happens when we try to do beta reduction to this proof? So this is something that's really fun to do actually. And the proof actually, one discovers that the proof becomes more and more complex when we try to understand it. I mean, this is because we have a paradox. So to conclude, I mean, this paradox is not surprising because it's intuitive that system F doesn't have a set theoretic semantics. And Girard found out that we can apply it to type colon type since we can translate type colon type in this extension of system F. Okay. And then, so with respect to the calculus I was studying, this means that we cannot add an extra level that is impredicative. So like type 1 with an impredicative quantification of level type 1. But still we can add a new level type 1 if it is predicative. And so that's the calculus that we get. So with this hierarchy of type level, so like in Agda, but this hierarchy is predicative. So it's only the base type, base universe, which is impredicative. And there is a set theoretic semantics. So this is, if we believe in set theory, then this calculus is consistent. And yes, so one can compare this calculus with set theory. And so one thing, for instance, that's interesting is that this calculus look purely logical, but it's possible in this calculus to actually prove infinity axiom. Okay, so we can do a predicative version of the encoding of natural number, and we can encode natural number, and we can prove that 0 is different from 1. But still, we cannot encode natural number in such a way that we get induction principle. So I think I will skip this part actually. Yes, and I will try to conclude actually. Yes, with this predicative impredicative. So yeah, so all this suggests actually it was when we had done this extension, I mean, because of this problem with predecessor and induction not being derivable, why not adding data types as primitive in Martin-Löf type theory? So that was what was done at the time. And so if we allow inductive definition, so Girard paradox actually becomes very, very simple because we can use these types to encode paradoxical types. So it becomes even simpler than Hurken's paradox. So we get a system so that combines ideas from Automat and Martin-Löf. So I spent a lot of times, I mean, trying to implement inductive families as primitive. So, I mean, my feeling, and it's still at the time, and my feeling now is that, I mean, this is definitively less elegant than impredicative encoding, because we have to introduce arbitrary syntactical restrictions. And so, I mean, there are still some work that needs to be done. But on the other hand, I mean, this impredicative encoding, which is so elegant, I mean, it doesn't work completely. So, I mean, there is a question that's, I mean, still very relevant today, and I mean, we still don't know what to do with data types. So there is a work by Onsedil that is very interesting, that tries to get a good encoding of data types using ideas from system F, and using another encoding of natural number, where we have a nice representation of primitive recursion. But I mean, all this, it's still work going on. And also, so after all this time, so is this impredicative type prop crucial for representing proofs? I mean, so in practice, so most proofs in mathematics don't use impredicative in an essential way. So it's very seldom that you have a proofs in mathematics that needs impredicativity. But in practice, I mean, it's used, but more used as something which is convenient. So it's convenient to have this big type prop where you put everything, rather than trying to understand more in details what's going on in the proof, what's going on in the argument. So I think what has been going on so far is that, so it has been very convenient, but not essential to have such a type. For instance, I mean, in this proof of four-color theorem, that was very helpful. So not essential, but I mean, it was simplification. So something you don't want to think about in the first approximation. And actually, there is the same questions for programming. So in programming, so they use F omega, but is this in predicative use essential? That's something that should be analyzed further. But this question, so it has changed actually recently. So with work on univalence, actually, and with the fact that the proof systems becomes powerful enough, so we should be able, and we should try to represent argument from category theory. There we need to deal with universes. So we cannot, I mean, this simplification, simple way to have an impredicative sort doesn't work. And Girard's paradox, I mean, shows that it's necessary. So we cannot have an impredicative sort for dealing with problems in category theory. And I think so the recent, so I don't know when it was introduced actually, so maybe Andreas should tell us. I mean, the universe level system of Agda, that seems to be a really nice solutions for this. So that looks like a really nice combination actually of predicativity, but flexible enough so that we get a good system. And but this is still, I mean, work in progress, so it should be explored if it works. This works really for representing argument in mathematics. And I think, yeah, I should stop on this. So thanks for listening. Yeah.
Thank you. I don't know if you have any more time, Thierry, if you want to entertain questions, but otherwise.
Yeah, I mean, if there are a few questions, yeah, I can, yeah.
Feels free to go, but I'm certainly
5 minutes questions, yeah.
Yeah. Stop the recording now.
Yep.